Okay, in this video, we're gonna continue discussing about the Lewis structure of covalent compounds. Let's take a look at another very commonly seen chemical. Excuse me, carbon dioxide. Okay. Now, carbon dioxide contains one carbon, two oxygens. So the total number of valence electron is uh, carbon has 4 valence electrons and the oxygen has 6 valence electrons. Okay. About number of valence electrons of the elements, okay, you really have to um, make sure some numbers are etched to your mind, okay, to your brain, like such as carbon, oxygen, nitrogen, this kind of commonly seen elements. Okay, you really have to know how many valence electrons they have. Carbon and oxygen, but there are two oxygens. Make sure don't forget to multiply by two oxygens. So you would have 16 valence electrons. Okay. Now there's one carbon and two oxygens. So I would put the carbon in the middle and then oxygens on the sides. Okay, so OCO instead of putting OOC or anything like that. And you have to connect the surrounding oxygens with the central carbons by one covalent bond each side. All right, so that will take away 4 electrons. Okay, so you would have 12 valence electrons left over. Now I can't over address this. Okay, you really have to work out one surrounding atoms and one of the surrounding atoms, and then work out the other surrounding atom, and then you work on the central atom last. Okay, the order cannot be mixed up. And the other thing is, once you count total number of valence electrons, okay, then it's irrelevant that how many valence electrons you had before. Okay, like oxygen here, you had 6 valence electrons. Carbon had 4 valence electrons when they were single elements, but that doesn't make either carbon and oxygen with higher priority to get 4 valence electrons, 6 valence electrons. It doesn't. Okay, it's like everybody contribute to this total valence electron, and that's it. Okay, how do you contribute more than the others or less than others? It doesn't matter anymore. Okay, at the end, everybody has to have the 4 pairs. That's it. Okay, so currently we have used 4 electrons by putting down two bonds. You have 12 electrons. Let's work out one oxygen first. Now this oxygen on the left, it has one bond, which is a 1 pair electrons attached. So it needs 3 more pairs to complete 4-octet rule. Okay, so let's put down 3 pairs. Symmetrically, this oxygen will also be needing 6 electrons, which is exactly what we have, right? 6 plus 6 is 12, so that's it. So let's look back at the structure again, okay? The one thing you can always double check if your structure is correct or not is, one, have you used all of the electrons, right? So yes, I have used all the electrons. I didn't overuse it, okay? You can't put more dots than what you have. So 16, that's all you have. Second of all, does everybody in the structure have 4 pairs? This oxygen does, and the carbon does not. Carbon has only 2 pairs, okay, if you look at the structure, two bonding pairs. So the only way to fix this is to actually move one of the lone pair, since you don't have any more electrons, okay, so you can't put more dots here. If you put more dots here, then you're using something you don't have. So in order to increase the number of pairs around the carbon, you have to move one of the lone pair to become a bonding pair. So you form a double bond here. But that's not enough, right? So this carbon now has 3 pairs. So you have to move another pair over. So it's not hard to imagine you have to move another pair over to become a double bond. So the overall structure will look like this: carbon with 2 double bonds. Again, we're forming double bonds because we ran out of the electrons. An oxygen has 2 lone pairs each. Okay, so each oxygen has 2 lone pairs, 2 bonding pairs, 2 lone pairs, 2 bonding pairs, and the carbon in the middle has 4 bonding pairs. But regardless, okay, they all have 4 pairs, so that's all you need. Okay, so one more issue we have to think about here is, now let me just give you a quick example first, okay? Now, for instance, this structure can be also manipulated in a way like we don't really form a double bond on both sides, okay? What if we remove another lone pair into here to form a triple bond on one side? So that will result into this. One lone pair, 3 bonding pairs for this oxygen, and this carbon will have 3 plus 1, 4 bonding pairs, and this oxygen will have 1 bonding pair and 3 lone pairs. Seems like this is also satisfying the octet rule, right? Without using extra electrons. So this is another possible structure, okay, based upon Lewis structure theory, okay. But in the reality, okay, in the real world, okay, this is the right one, this is the wrong one, okay. So I won't use this example to show you two things. One, you could have possibly two different structures, okay, by manipulating the double bond, triple bond, multiple bond, especially when you have multiple bonds, double bond or triple bonds, okay. This is called the resonance structure. Okay, that's one thing. The other thing is not all, like in this case, this resonance structure doesn't really exist. The only existing one is this one. Second of all, Lewis structure. What we have discussed is based upon octet rule. The basis, the foundation is octet rule. 8 valence electrons, but there's something else also contributing to the Lewis structure. So what we are learning right now, Lewis structure does not really give you 100% correct. Like based on Lewis structure, this one will be correct, but in the real world, it's not. So there's something else about the Lewis structure. Okay, you're gonna learn in General Chem 1. Okay, just keep that in mind. One thing is about Lewis structure. The other thing is called the formal charge, but that's not going to be in our discussion here. Just that you know there's something like that. Okay, so this is the Lewis structure of carbon dioxide.